Hello guys, welcome to today's video. In the last video I promised us I was going to show us one or two things on different equation. I did some oversimplifications. I kind of like abstracted a lot of difficulties in the last video, and I am going to expatiate on those moves that I made. So we were given the problem that we should solve the difference equation. And the difference equation we were given was y of n+1 and minus, we had n+1 y of n is equal to 2 raised to the power of n, and you have an n+1 factorial. And the initial condition is y of 0 equal to c. So we were given this particular question to solve. So I did a lot of things, and I would love to show you how I arrived at where I arrived. So let's dive in together. So you're given this particular difference equation and you want to solve it. As usual, you have to compare with the general first order non-homogeneous difference equation that difference equation is given to us as y of n+1 minus a of n y of n equal to g of n. Now, this difference equation have a solution that is given to us by this. The solution is y of n as general solution is equal to, I have my product operator I equal to n naught, then you now have your n-1, you have your a of I multiplied by your function y of n naught, that's your initial condition, then plus we have a summation, we have k equal to n naught to n-1, and we also have the product operator from I equal to k plus 1 to n-1. This acts on ai of I, rather a of I. Then you have to multiply this by your g of k. Okay, so this is the solution that we have, and I will still explain how we got this solution, but in another video. Now I just want to show us some rules and some important things that I believe you know before, but this video is going to be a refresher for you. So if you compare the equation that you're given to solve with this general one, you have to actually be able to pick out some important things, like a of n will correspond to n+1 in this case, and my g of n will correspond to what? 2 raised to the power of n times n+1 factorial. Is that okay? So when you make the comparison, you can now see that a of n is n+1 and g of n is 2 raised to the power of n+1 factorial. You also do that your y of 0 is equal to c, and this is how we usually depict our initial condition, which is y of n naught. And since our initial condition is equal to c, an arbitrary constant, we can say our n naught is 0. That's our starting point, right? So if you have these particular three parameters, then you can now substitute it into this equation over there to resolve and find the value of y of n, because y of n is the solution to this difference equation that we are looking for. So we are going to take it step by step. So your y of n is going to be equal to, now When you come to this first place, you have your product operator from I equal to n naught, then to n minus 1, then a of I. So my God, where do I get a of I from? It's very simple. You get it from the expression of a of n. You just need to replace n with I, and instead of I you have what? N, you have I plus 1. So the same thing happens when you get here. When you want to get g of k, you just have to what? Replace every n with k. Is that okay? So you have 2 to the k and k plus 1 factorial. So we've gotten what we want, so we can now replace it like this. So we have the product operator I equal to our n naught. Also, we have already resolved our n naught from the initial condition to be 0. So if you are very attentive, you will still remember how we did that. Our n naught is 0, then we now have n minus 1. Then we have our ai, which is n, which is I plus 1. Okay, then this is multiplied by our y of 0. Is that okay? Which is our y of n naught, and that is c. And you now have plus your summation from I equal to, not I, sorry, it's k. K is equal to n naught, which is 0. Then you now have n minus 1. Then you now have the product operator again. And you now have it acting from I equal to k plus 1 to n minus 1. And it acts on our ai, the same values, which is I plus 1, and the result is multiplied by g of k, which is 2 raised to the power of k, then k plus 1 factorial. So in the last video, I told you that I was going to explain a couple of things that I did here at this point to make some resolutions, and I'm going to do that now. So I'm going to break it down starting with this term. So we'll break it down so that we'll understand how to resolve problems like this. So when you're given something like this, so consider a pi from I equal to 0, n minus 1, then you now have an I plus 1. So let's open this bracket. The pi is the product operator. Is that okay? It's the product operator. So when we are talking about product operator, it means that whatever is here, you're going to keep multiplying it after each iteration. So each iteration, I equal to 0, I equal to 1, I increases up until it gets to n minus 1. So you're going to keep multiplying this same value. So for I equal to 0, I'll have 1. Okay. For I equal to 1, I'll have 1 plus 1, which is 2. Okay. You can see the brackets, which means multiplication. And for I equal to 2, I have 2 plus 1, which is a 3. So for I equal to 3, I have 3 plus 1, which is a 4. So I'll keep going like that. If I is equal to 15, I'll have what? 16. Is that okay? Then I keep going till I get to the last point, which is what? N minus 1. So when you put in n minus 1 here, you have n minus 1 plus 1, and you're going to get n eventually. So this is like an ascending case of multiplying numbers. We multiply number from 1 to n, and if you're familiar with your factorial, this is just simply n factorial. So the whole of this first part, the whole of this resolves to n factorial. Is that okay? So this will now be an n factorial multiplied by c. So let's go and break this down and see what we get. I'm going to write it in another part of the screen. So you also want to consider the second part, which is the summation from k equal to 0, and you now have n minus 1, and you now have the product operator from I equal to k plus 1 to n minus 1, and you now have your a of I, which is I plus 1. Okay, then everything here is multiplied by 2 raised to the power of k, then you now have k plus 1 factorial. Okay, so first of all, what we are going to do is we are going to consider this particular term here. So consider, again, I want to show you how this whole stuff is going to resolve to 2 raised to the power of k, then n factorial. So that's what the whole of this will resolve to. Okay, so let's do that proof together. Now, what you're going to do is you're going to consider again this particular term, pi from I equal to k plus 1 to what, n minus 1, then have I plus 1. So if we start resolving this product, this is what we are going to get. What we are going to get is when we have I equal to k plus 1, and you now have what, k plus 2, that's the first term. When I is equal to k plus 2, that means when we increment, okay? So you keep incrementing. For k plus 2, we'll have k plus 3 here. Is that okay? And for k plus 3 here, we'll have k plus 4. So for k plus 4, when you put k plus 4, that's the k plus 4th increment into this formula. You have k plus 4 plus 1, which is a k plus 5. So it keeps going until we get to k plus 16. So k keeps increasing, and take note, k is less than n. Okay, k is less than n. So it keeps increasing until we get to the last value of this particular iteration, and the last value is n minus 1. Now, when the last value is n minus 1, when you plug it into this formula, what are you going to get? Very good. So you have I, instead of I, you have n minus 1 and plus 1. This cancels out and you're just left with n. So that means the last value in this multiplication will be n. Now, if you're very sensitive, if you're a very sensitive mathematician, this is what you will get. Okay, so follow me. So we have resolved this particular part of our product. That okay? So after resolving it, I want to put this inside here and merge it with this one and see what I'll get. So I have my summation k. It's actually k. Okay, so you now have n minus 1. Now in this place you have remind me again, very good. You now have your product operator, that's this one. So I want to substitute it with this that I have gotten and mix it with this one and see the beauty that I'm going to get. So I'm going to copy it. For my product operator, I'm going to have a k plus 2, a k plus 3, a k plus 4, and a dot dot dot, then finally I now have an n. Okay, so this is the outcome of the product operator here. Then the next thing is actually this one, 2k, 2 to the k, then k plus 1 factorial. So you have 2 to the k and k plus 1 factorial. Now, let's observe what is happening here. So if I give you a number like 9 times 8 times 7 times 6 times 5, okay, you know that this highest number is 9 and it's going down. So what is missing? You agree with me that what is missing is actually what? A 4 factorial is missing. That okay? So if I were to write this number the way it is right now in terms of 4 factorial, I'll say this number is still the same thing as, if you're going to agree with me, it's going to be 9 factorial divided by 4 factorial. Okay, so this whole product like this that you're seeing is still the same thing as you saying 9 factorial divided by 4 factorial. So when we get to 5, we know that we're supposed to do 4, 3, 2, 1. Very good. And definitely this particular place has now captured it, because if you expand this, you're going to get 1 times 2 times 3 times 4 times 5 times 6, 7 times 8 times 9, divided by 4 factorial is actually your 1 times 2 times 3 times 4. So this whole section of the multiplication, sorry, is taken out. You understand? And you're now left with 5, 6, 7, 8, 9. That's what we have here. So that's the same thing that is happening here. If you look very closely, now I have a k plus 1 factorial. Remember, before k plus 2 is k plus 1. It's just like saying before you get to 5, you hit 4. So do you know that the whole of this particular thing here is still the same thing as someone saying summation k equal to 0, then n minus 1. The whole of this thing, since the highest number is n, is still the same thing as you saying n factorial divided by k plus 1 factorial. Because when we spread n factorial until we reach to k plus 2, then k plus 1 factorial, we'll now be left with what you have over here. Like if I spread this thing, I'll have n, then I keep going down. I keep going down till I get to my k plus 4 and my k plus 3 and my k plus 2, then k plus 1 factorial. Is that okay? Then divided by k plus 1 factorial. So if this cancels out this, you're now going to be left with from here to here, just like we have here. So the whole of this product is still the same thing as someone saying n factorial divided by k plus 1 factorial. And you now have times 2 k, then you now have another k plus 1 factorial. Is that okay? So this can now cancel out this. Okay. And finally, and it cancels out, you'll now be left with sigma k equal to 0, n minus 1. Then this times this is now what gives you your 2k and your n factorial, or your n factorial 2k, just like we proved over here. So anytime you see a problem like this, okay, this is how the 2k times n factorial was obtained. So you used your knowledge of mathematical induction to derive until you get to this point. So if this looks a little bit challenging, you can pause the video and go over it again at your pace. Is that okay? So what do we do from here? So let's wrap up the question again. So in wrapping up the question, so far we stopped at this place. We stopped over here. We've gotten the solution of this first part. Now we've able to simplify this part, and what we have is summation 2 to the k and n factorial. So from k equal to 0 to n minus 1. So I'm going to find the solution further from this point. Is that okay? So let's go. Let's go together. So what do we have? What do we have? So this is what we're gonna have. Okay, if you're following me. So if you're following me, our y of n is going to be n factorial multiplied by c, and plus summation k equal to 0, n minus 1, and you now have 2 to the k and n factorial. So let's move further. So we still have work to do on this place. Is that okay? So if you are with me, let me break down this one again and see what we'll get. So if you resolve this, consider before you resolve this, okay, let's do something first before we resolve this so that it will be easy. So you have y of n, then you now have n combination and n factorial, then you now have c is a constant, then plus. Now this summation is actually counting in terms of k. So since it's counting in terms of k, this 2 raised to the power of k will be what? Changing each time our k changes the variable it's holding. But this n factorial is not being affected by this summation counter, so it can come out from the summation as a constant. So you now have k equal to 0 and n minus 1, then you now have what? 2 to the k. So this whole stuff is still the same thing as this. So my emphasis will now be, what is the value of this particular expression? What is the value of this particular expression? So this is really very easy to solve if you can remember some principles you learned. So consider you have summation k equal to 0 then to n minus 1, and you now have 2 raised to the power of k. So let's expand. We have 2 raised to the power of 0, and you now have plus 2 raised to the power of 1 plus 2 raised to the power of 2. So k keeps increasing by 1 each time, and plus 2 raised to the power of 3 plus dot 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 plus. So the last term will be what? When n is equal to what? Sorry, the last term will be when k is equal to n minus 1. So we'll have 2 raised to the power of n minus 1. So if I ask you how many terms are between here and here, what are you going to tell me? Someone will immediately shout n minus 1 terms. But if I ask you how many terms are between 0 and 9 inclusive, someone might shout 9 terms, but there are actually 10 terms between 0 and 9. So anytime we're starting from 0, and we see the upper bound of our counting as n minus 1, the total number of terms between 0 and that particular last term is actually what? N. Okay, so you have to what? See that it's actually n, because n minus 1 is just like you counting from this first term to the n minus 1 term. Then the 0th term now contributes 1 to it, making it n. Is that okay? So from this term to this term is not is not n minus 1 terms, rather you have n terms to deal with. Is that okay? So since we have n terms to deal with, this is a series 2 raised to the power of 1 of 0 is 1, then I now have 2 plus 2 square plus 2 cube plus 2 4 plus dot dot dot, you understand, plus 2 to the n minus 1. So this is a geometric series. I remember the sum of a geometric series is given to me as a into what? R minus 1, r raised to the power of n minus 1 all over r minus 1. Okay, the sum of the first n terms of a geometric series. So the sum of the first n terms of a geometric series. So I am having n terms in this case, and I want to find the sum of these terms. I need to find my a, which is my first term, is 1, and my common ratio, which is actually difference between the ratio of the second to the first or the third to the second. And if you check very well, you're going to get 2. So since we are finding the nth sum of this particular stuff, our Sn is going to correspond to my summation k equal to 0 and n minus 1. You understand? That's the nth sum of this particular expression. Then you now have your 2 raised to the power of k. So according to this formula, a is 1, that's the first term, and you now have what? R raised to the power of n, giving you 2 raised to the power of n and minus 1 divided by 2 minus 1. So in the last video, if you noticed that I said that summation k equal to 0, then you now have n minus 1, 2 raised to the power of k results to 2 raised to the power of n minus 1 over 2 minus 1. This is exactly how it was proved. So using our knowledge of arithmetic and geometric progression, precisely geometric progression. So if you resolve this, you're going to get 2 raised to the power of n minus 1 divided by 1, which is 2 to the n minus 1. Okay, so this is the sum of your terms. So generally, keep this formula in your pocket. Whenever you have a sum k equal to 0, then you now have n minus 1, and you sum a raised to the power of k, where a is a constant that is not equal to 1, then you're not going to have what? For general, a raised to the power of what? N minus 1, then all over a minus 1. So that will be the answer for this summation. Okay, any summation of this form is going to be like this, and a is taken as an arbitrary constant. So now that we've gotten it, we can now go ahead and round up our answer from this point. So our y of n was formerly n factorial, then c, then plus summation. You have k equal to 0, and you have n minus 1, and I have n factorial, then you have 2 raised to the power of k. So this became n factorial c plus n factorial comes out. You now have your summation k equal to 0 then to n minus 1. And you now have 2 raised to the power of k. So you had n factorial c plus n factorial. When you resolved this one, you got 2 raised to the power of n minus 1. That was what we resolved when we got to this point. Or if you want to still go back and do the maths by yourself. Is that okay? So at the end of the day, we now had n combination, n factorial, then c plus n factorial. Then you now have 2 raised to the power of n minus 1 in brackets. So you can now what? Factor out the n factorial. So your y of n will be n factorial. Then you now have c plus 2n minus 1. Someone can stop here, or someone can stop like a professional maths will want to bring the number first, then the constants can now interact with themselves. So someone else might be mad enough to say that c minus 1 could be another arbitrary constant d. So he might leave his answer like this. And so on, then you now have 2 raised to the power of n plus d. Well, if you want to do that, no problem, but I won't advise you to do that in this particular situation. Let's just stick with our original and our original c. And remember, c is your y naught as your initial condition. So your y of 0 is also represented as y naught sometimes. Okay, y naught is actually y of 0, and this is it. This is it pretty much. So the summary of this video is that we've learned how to actually resolve some complex summations. So when you encounter problems like this in the exam or in a test scenario, try to break it down gently. Definitely you're going to figure out a pattern that you recognize before. Then you can use any knowledge that you know before, maybe from factorials, or maybe from arithmetic progression and geometric progression, or maybe from even law of indices. So actually resolve this summation parts. Okay, so there is one thing with these equations. One thing is memorizing the formula that's for the general solution, and another thing is having your way to be able to manipulate and solve and resolve the summations till you get your final answer. It's not really easy at first. It took me time to actually master it. So it might also take you time, but I assure you that if you practice 1, 2, 3 times, your hand is going to get familiar and you'll be able to solve different questions. So thank you for watching this video. I am still going to solve more questions on different equations, questions that perhaps you might probably anticipate for exams, and I still promise that I'm going to create a video where I show you how to derive the formula for both homogeneous and non-homogeneous solutions to different equations. That's this big formula that you see. So I'll still bring out that video, but in the meantime, I want you to memorize this particular formula and learn how to use it. Go to the last video and watch how I solved 3 different questions, and with that you should prepare yourself for multiple questions that I'll be laying out. So thank you for watching this video once again. It was a long one, but I hope you now understand how it became like this. So like, subscribe, share, hit the notification bell to stay updated. So the next video, stay blessed. Bye.